Okay. Good morning, everyone joining here in person, and hello to everyone on Zoom. We're going to have this tutorial, which we were still confused when it starts, 8:30 or 9, but it is somewhere between 8:30 and 9. We're going to get started. This is on conversational agents, specifically proactive conversation agents. We'll tell you all about it. Our tutorial is divided up in 3 parts, and we have 3 people here presenting. And so we'll first start with our quick introduction, and then we have divided up these 3 parts among 3 of us. We also have some interactive exercises, and we'll figure out how to do that, both those who are joining in person as well as those who are joining on Zoom. So we'll start with Lizzie.
Oh, hi, everyone. I'm Lizzie Liao from Singapore Management University. It's our honor here to present our tutorial about proactive conversational agents. Yeah, and we have, I do about conversational AI. Now I'm focusing on proactive conversational systems. Do a lot of topics such as active ontology expansion and topic shifting, and also response generation. And I use the multimodal conversational system as the kind of application end. Yeah, so let's introduce another of our speaker.
Hello, I'm Grace Hui Yang from Georgetown University, Washington, United States. I grew up in Singapore, and I graduated from National University of Singapore. I used to work with Professor Tenzin Tra for my master thesis. So it's really great to coming back home. So today we'll talk about proactive conversational agent, which is a topic really excited. It's really exciting, and the 3 of us we really love to work on that, and I want to share with you the latest state of art and some good discussion and future directions.
Thank you. And I'm Chirag Shah, I'm a professor at University of Washington in Seattle, US. I work in conversational systems, again, more from the proactive side. So I've done work in proactive information retrieval. It's funny how much things have changed even since we submitted this proposal for tutorial. As we all know, things like ChatGPT and BARD and a lot of things have come out. That has only intensified the need to study these systems and how important they are and how much they are starting to change our lives. So I'm very glad you're here because we're excited to share our perspectives on this, but also keep in mind that we are all still learning. So a lot of things that we are discussing, they're not settled, they're not concluded, they're not done. And this is a very active research area. So one thing as we introduce ourselves and we put this warning is this is an emerging research area. And so things that we might even present as conclusions are not set in stone, right? That they are still kind of changing. As I said, even between putting this proposal in to having it accepted to planning for it, a lot of things have changed. So things are shifting, not just on a yearly or monthly basis, but weekly basis. And even in today's tutorial, we'll see some of the things that we hadn't originally planned for. We're going to cover them now because they have become very relevant. So here's our outline. As I said, we have 3 parts. The first part is just giving an overview of this area. As I said, we will also do a little bit of exercise and we'll figure out how to do that both in person and on Zoom. The second part and third part will go into details in depth for some of the things that I'll just briefly mention in the first part. And so you'll get to learn about how we could actually do, what are some of the existing techniques we have for making proactive conversational agents. So let's start with the introduction, just to kind of take a quick look at where things have been. And so here's a brief history of conversational agents. And And we're kind of starting from the early days. Many of you may know ELIZA. Has anyone heard about it? The first text-based chat system. I think now it's part of a museum of computer science, because this is really a landmark thing. It was there in the beginning years. So ELIZA was it's kind of, you see as the black and white old days with the text-based conversation. It was a rule-based system. So essentially the program was written in a way that had hard-coded things where if the user says X, you respond with Y, right? And so those were the early days. In fact, I kind of remember a few years after this, I wrote my first a conversational agent, and it was basically the same kind of stuff, where it's a long program with a lot of things just hard coded, right? There was a little bit of stochastic things in it in terms of when user says X, sometimes you respond with Y, but other times you respond with Z, but pretty simplistic, still very deterministic, way. Of course, things took off in the early 21st century. I mean, so you can see there's a kind of a big gap from there to the next phase, which we're putting, things like Apple Siri. But the big thing you can see changing here is the modality, right? So early conversational agents, not only they were rule-based, but also they were textual. But then you start seeing this new phase where some form of machine learning is involved along with rule-based. So there are still rule-based things, but more importantly, now we have changed the modality. So now these things start becoming more of the audio-based, auditory, right? So we all have some connection to one of these systems, whether it's Siri or Google or Alexa or Microsoft. There's been a bunch of them. Samsung has them as well. So these things are kind of a mixed systems where they're using rule. Specifically, if you think about like Siri in the early days, they had this knowledge base that's based on Wolfram platforms. So those who are familiar with MATLAB, that's a Wolfram system. And so that's a huge knowledge base where you can query things. For instance, if I want to know what is on the other side of the planet from Singapore, right? So that's a query that you can actually pose to this Wolfram, system, and it can actually answer that. So a lot of those kind of things. So those are, you can say, deterministic, query-based, rule-based things. But then also a lot of things that are not going to be as straightforward. So these systems combine those prompts. And then we start seeing this proliferation of these personal assistants, whether, it started with Siri, but there's a lot of other things. And then we enter this new phase in somewhere around 2017, 2018 or so, where we start seeing transformers. Now, this is a landmark architecture. As you know, those work in machine learning. And a little bit of this we'll talk about even today, where this really changed the way we do machine learning in general, but then certainly in terms of natural language understanding and natural language generation, right? So we start seeing a lot of this pre-trained models. And again, we'll talk about that today as well, large-scale language models, where you have a big corpora from which these models train. And then once they're trained, they can be then applied to different applications with proper kind of fine-tuning. And so some of the famous ones are LLMs are from Google's Mina, OpenAI, GPT-3, GPT 3.5, and soon GPT-4. Transformers really change the trajectory of what we can do. Right, so these things now just took off, and if you see where things are heading, like this is where we are now. And in fact, today also we'll focus a lot of things that happened just a year ago or even a few months ago, because things have changed so much. And it's important that when we study these things, we're not just looking at this broad history, which is still important, but really looking at where things are. Things like Lambda. from Google, and then ChatGPT from OpenAI, Google's Bard, Ernie Bot from Baidu, and so on. So this is where we are, where again the approach has been very different. It's no longer rule-based. It's also not just any kind of machine learning. It's starting to use a lot of deep learning models, a lot of reinforcement learning. They're starting to use mostly large-scale language models, large language models. And so there are, this is where we are. So this is sort of the brief history and the main phases of this, right? Now, as I said, a lot of things have happened more in the recent years. And so it's important even just looking at the recent trends, right? In just the last year or so. So there are two kinds of things we notice here. These chat bots or conversational agents, they're doing things either for solving tasks or personification, right? So solving tasks, you can put things like ChatGPT, and we'll talk more about it in a few moments, and Anthropic AI, it's a cloud. So these things are designed to address specific kind of tasks, right? You can typically do a lot of conversations around task solving, problem solving, and so they're really trained with the kind of knowledge bases you'll need to be able to address those kind of factual and other kinds of tasks. And then there are these companies that are doing personification. So this is where you have agents that are more designed to be mimicking a person, right? So they are, it's important in those cases that they actually look and act more like humans, and they have a different purpose. So we'll talk about it. Often in many cases, people are looking for emotion support, right? So solving tasks is of course the number one or the biggest category here. Things like, can you help me book a restaurant for two? Right? So that's your task. You want to make a reservation, and then you're having this conversation. You're using this agent as your personal assistant. So you can see some of these things that are either in the traditional information retrieval sense, they're either kind of navigational or informational or transactionals, right? So some of these things are about finding information. Some of them are executing things, but you're using the conversational, you're having conversation with this agent, and the agent is acting as your personal assistant, right? Plan a 2-day tour to Singapore, right? So imagine if you had a personal assistant, you could make a request like this. And of course, this is a big task, right? I mean, but presumably your personal assistant will know enough about you, your priorities, your preferences, your budget, things like that, to then sketch out that plan. So it goes beyond just finding some information. And then the other category, as I said, is where you want to have a conversation as not necessarily finding information, but the kind of conversation that you will have as part of emotional support, right? It's the kind of conversation you'll have when you're just hanging out with a friend, right? Or and there are special populations, for instance, elderly people, and they want to have the conversation as part of their mental well-being, right? So it's raining outside. I'm kind of feeling lonely. Now, it's not necessarily, this is not a fact-finding thing. This is not a transactional thing. But you can imagine if a fellow human being were to say something like this, you understand that they're looking for some company. They're looking for some conversation just to kind of, in that moment for their mental well-being, right? So a lot of these things, and these are becoming quite important. One of the reasons is these agents are starting to have that capacity to understand, right? So they say the first thing, it's raining outside, I'm kind of feeling lonely. In a traditional information retrieval sense, there is no need expressed. There's no query, there's no question. But we're starting to have natural language understanding in a sophisticated manner that can parse that as a need for emotional support. So this is actually becoming very important. And in fact, this is where you can see the need for personalization and need for proactiveness, right? So again, for humans, this is very natural to do. When somebody says that statement to you, you kind of understand what's happening here, and you're able to provide that sympathy, you're able to provide that empathy, you're able to provide some support without the person explicitly asking. And keep this in mind. This is part of our definition for being proactiveness, for being proactive. That this is where an agent is able to offer something without the user explicitly asking for it. So when it comes to emotional support, the proactiveness and personalization becomes even more important. So there are many ways to slice and dice the conversational agents we have today. This is one way. Another way we can think about them are, again, task-oriented and just open conversational agents. So task-oriented, and we're going to go a little bit into details for this. We'll talk about both of these. But here's a typical task-oriented conversational agent. You have input from the user. And this input, we're assuming it's going to come in some kind of a natural language, right? So it's not coming as a bunch of keywords like a typical query, but it's coming as a statement, as a question, something in natural language. So the first thing you need is a natural language understanding, or NLU. So that's the first module that's typically put in place here. The next thing is what's called state tracker, and we'll talk about it a little bit in detail. So this is where you're trying to understand, trying to parse that the question or the statement that came in to where the user is, where it's leading to, right? And so state tracker is come into place, and it's able to use something external, some external knowledge base, right? It could be from Wikipedia, it could be from Yelp, it could be from search engine, some external source of knowledge that it can use to figure out how to respond. Right. So once again, we'll talk about each of these blocks in details. Dialogue policy, that's the next block, and that determines how to construct the response going back to the user. Right. So this could be based on some rules. This could be based on some machine learning algorithm. And then finally, once we figured out, given this request, given what we know where the user is, given what the external source knowledge is, and we determine what to give back to the user, we want to give that in a natural language because the request came in natural language. And so the final stage here is that of natural language generation. And once again, here, this is where we can see a lot of the recent advancements playing off, starting with the transformers, because it allows us to generate these natural language responses. So we'll go into some detail of that as well. We'll reserve this open chat thing for some later stage, but for now, I want to go into that the task-oriented chatbot, right? So again, there are these stages. Let's say that we already kind of figured out how to do the parsing of the input and understanding what the user is saying. So then we're going to go into these three blocks of and see what that means. So here's the first thing, the state tracker, right? State tracker, and I'm going to explain this using an example. It requires two main things. One is detecting the intent, and then the second is detecting the slot and value. So what do I mean by that? Well, imagine here's a request. Find a good eating place for Chinese food, right? So that's a request that came in from the user. And imagine you have that your natural language understanding module that is able to understand, parse this. For state tracker, the first thing you'll do is figure out what is the intent. So in this case, and I'm not telling you right now how exactly you do this, but imagine you have some process, some way to do that. What you're going to do is intent classification. So this is essentially a kind of classifier that's going to figure out that the intent here is find restaurant. And imagine these are other possible intents. So if you have a set of finite intents, you can say, okay, well, from this request, which intent does it classify in? Which intent does it fall in? So intent here is find restaurant. Okay, so you detected that from this. The second thing you do here is what's called slot filling. And here, slot essentially, think about this as variable and values. right? So the variable here could be, rating or type or number of people, area, right? So this could be a predetermined set of slots. And what you're trying to see is, okay, from the request that you got, do we have values for these things, right? So you can see that from the request we got, find a good eating place, right? So we can say, well, we discovered that good is associated with the slot rating. So something with a good rating, right? Type, what kind of type food you're looking for? You're looking for Chinese food, right? We don't have information about number of people, which area, so that's unknown. But at least we determine these values for these slots. Okay. Now, once you do that, you realize that you have now almost like an SQL query that you can execute. And it kind of looks like this. So imagine you have a function that is essentially a mapping of your intent, find restaurant. And that takes a bunch of values or parameters. And in this case, these are the things that you figured out, that the rating should be good and the type should be Chinese. But of course, you could have other parameters too if you have figured out. It all depends on what you got out of the user. Right? So state tracking module essentially covers tracking or detecting or identifying or classifying intent, as well as filling out as many slots as you can. Now, of course, sometimes you realize that you don't have enough value for the slot. So let's say you determine the intent, right? So the user could say, find me a restaurant. But you realize that in order to execute this function, you need at least some parameters. I mean, this is similar to what you would do with a human being, right? If somebody here would like, hey, I want to go out for dinner, can you recommend a restaurant? What would you do? I mean, you might want to at least find out, okay, well, what do you like? Are you looking for something in walking distance from here? Are you looking for like vegetarian option? You're looking for, something of that sort. Or you can make assumptions that when somebody says, I'm looking for some restaurant suggestion, you can assume that they're looking for something that's, close enough. They're looking for something that's with good ratings, right? But somewhere you have to figure out either by asking the user or through your own assumptions, if you don't have all the slot values or enough slot values detected or extracted from these things. But that becomes important part here. So the end result is something like this, right? Which is almost like an SQL query. Then you need to figure out, okay, well, now that we've determined this, we want to communicate this with the user. And in some case, we want to actually ask them a question, a follow-up question, right? So how do you figure this out? So this is where your dialog policy comes in. What we want to do here, so imagine this is what you figure out, where you said, okay, well, we detected find restaurant as an intent. So that's almost, it's like a function. And then we detected these slot values. So those are sort of the input to the function, the rating being good and type being Chinese. But that's not enough. I also need to know what is the price range you're looking for, right? So in other words, having figured this out from the user request, now you want to ask the user about area and price range. Okay. So how do you do that? How do you figure this out? So this is where you have different approaches. The simplest one is the rule base, right? So this is where you would have some rules which says that the best way you can execute a request like this intent or this request is you need to know area where you want that restaurant, you want to know the price range, you want to know the type of food, right? And so you need to have this thing. And since you don't have all of that, ask for whatever is missing. So that's a straightforward approach. That's a rule-based thing. As you can imagine, these rules are handcrafted, but they're not scalable because we're talking about only one intent, finding restaurant. You can imagine there being lots and lots and lots of intent. And for all of them, there could be all kinds of different parameters. And then somebody still has to make a decision about what parameters are required, what are optional, and so on. And you and I can disagree on them, right? So It's not very adaptable. It's not very scalable. The good thing is, I mean, it works, right? I mean, anyone can easily design these rules, whether others agree with them or not, whether they're scalable or not. You can start coming up with these rules. These rules are also explainable, right? And this is another good characteristic of a lot of these rule-based systems, that anytime when somebody said, well, why did you ask me this? Well, there's an explanation for that, right? You can actually easily debug it. You can trace it and explain why did I ask you for area and price range, right? Because I have learned that to recommend your restaurant, I need to know these two things. But because of their limitations, it's not ideal in many situations to create or keep coming up with rules for all kinds of intents. So we can also use some machine learning things. Supervised learning is the first thing, is more straightforward. This is where, imagine if you have enough corpus where you have these kind of answers that you can learn, right? So imagine you have a corpus of conversation between people. Specifically imagine there is a concierge at the hotel. The concierge gets these kind of requests all the time. People ask, can you recommend some restaurant? And the concierge in return asks questions like, okay, well, what is the type of food you're looking for? Are you looking for somewhere you can walk? What is your price range, right? And then respond. So imagine you had a corpus of those conversations. The hotel patrons having this conversation with concierge. From that, you can learn that here's what we should be asking when somebody says, I'm looking for a restaurant. So this is almost like you're shadowing that concierge or customer service representative and learning from their behavior how they respond when they are able to look something up and give the answer, when they are following up with a question and so on, right? So you can do that in supervised manner. And then finally, reinforcement learning. This is where it's more of a trial and error, right? So what you're trying to do here is, obviously you probably wouldn't do first in a live system because, but imagine you're able to do that with an offline system where say, okay, well, in response to this thing, I can just give you a recommendation for a restaurant, but it turns out that that's not good enough because I gave you a recommendation for a restaurant that's really, driving distance and not walking distance, and you wanted to walk, right? So if I make enough of those mistakes, I learned that, well, I should really first ask you where you're looking for this restaurant, right? So that's a reinforcement learning approach where you learn through trial and error and through trying to optimize the reward that you get from this conversation. And so that's so the good thing there is you don't need rules. You also don't need this kind of supervised approach with a lot of corpus, but you do need a framework through which you can do this trial and error thing. So finally, the generation module. So imagine now somehow, through your previous processes, you figured out that you need to do this. You need to ask the user for, hey, what area you're looking for and what price range, right? And so that's what you figured out. And from that, you want to turn into a natural language response. So something like, where do you want to go? Any price range requirement? Or do you have any specific location in mind? What price range, right? Both are acceptable. Both are natural language responses. And you need to generate this from this internal representation that you have. So how do you do that? Again, the simplest approach, straightforward approach is template-based. So this is where almost like a rule-based system, you have a template of how to interact with the user asking for more information, right? So you can say the template is, what is X? And then X is coming from these parameters, right? So, what is the area you're looking for? Or what is the price range you're looking for? So I could just have a template for asking for more information. And then I just plug in the parameters that I don't know, the variables for which the value I don't know. And that just generates the the response for the user. So that's the end of our loop. But of course, like the rule-based systems, that has its limitations, right? I mean, it can only take you so far. It's not very scalable. So there are other approaches where you can learn these kind of things. You can learn how to map these to natural language sentences. So there are statistical approaches, and there are also transformer-based approaches. And this is where we're going to spend some time today. So I won't go into it right now. Okay, so that kind of completes our loop for task-oriented chatbots. And then there is the open chat models, which is where I think we're going to spend some more time later today looking at these different techniques. But just as an overview, in both, there are two approaches for the open-ended or open chat generation models. One is retrieval-based and the other is generation-based. In both cases, you have input from the user, X, and then you have context. So remember, unlike the task-oriented thing, here there may not be a specific problem to solve, right? In the previous case, the task-oriented thing, the request came in as, find me some restaurant with good Chinese food. So that's a task-oriented thing. Here, it could be simply, I don't know what to do in Singapore today. It's raining, right? And so there's kind of a task in that, but it could also be just like, let's just talk about it. I don't know where we are, right? So there may not be a specific explicit need or expression of task, but it's simply an input that comes in. But then there's also context, right? So you can derive the context from this, or you may already know the context that the user is in Singapore, that currently it is raining or something like that. In both the cases, so if it is a retrieval-based thing, then essentially you are doing a typical retrieval thing, which is just like how you would take a query and look through the documents that you have for matching, retrieve those possible candidates, and then you do the ranking. Similarly, imagine here you have a data set or you have a repository where when somebody says, I don't know what to do, it's raining today, or it's too cold to go outside. Things like that. What are some of the possible candidates? Right? You retrieve them, you rank them, and then in most cases, you just provide the first, the best ranked response as the output. And in case of generation-based technique, you are not retrieving anything, but you're actually generating. So you already have a model that's prepared to generate natural language responses. And typically this is transformer-based. So there is some kind of encoder, there's some kind of decoder, right? We'll go into detail here. And those who are familiar with the encoder-decoder architecture probably already know this. But essentially, you're looking for, in simplest term, you're looking for completing a sentence, right? So when, say, today is raining, I don't know what to do. Okay, how about we do what comes after that? And so you may have learned this from a large corpus from which you build your language model, and what is the most likely candidate for finishing that sentence, given the input and the context. So you still have the input and the context that is encoded here, and then you're generating this response. Okay, how about we do what, right? And so that's the approach here. In both the cases, there are issues though, right? And you have to remember that here we're talking about open-ended conversation. There may not be a specific goal. We're just having a conversation. A lot of things could go wrong. Here are some categories of things that could go wrong. So there could be semantic issues. Here's an example. A user says, I came from Shanghai, or I come from Shanghai. And machine says, cool, I'm from Beijing. We come from the same city, right? So it missed this idea of matching here. User says, back to Beijing now. It is so cold, but I'm very happy. And machine says, when will you come to Beijing? So again, the machine misses this information that the user is already in Beijing. It caught on to the idea that the user visiting Beijing or coming to Beijing And instead of seeing that it was actually a done thing, back to Beijing now, a human being will understand that that means they're already in Beijing. The machine says, when will you come to Beijing, right? There are consistency issues. So this is where between different responses, machine is not consistent. The agent is not consistent. User says, are you a boy or a girl? Machine says, I'm a boy. And then when the user says, are you a girl? And the machine says, yeah, I'm a girl, right? So what's happening here in this case, the agent is only looking at the current question that is posed. It has not looked at what has already been answered. So since it's already answered that it is a boy, then saying that I'm a girl, it kind of is contradicting or lack of consistency. And so it's not able to, keep track of it. So this often happens with generation-based thing. And finally, interactiveness issues. So user says, terrible breakfast today. Machine says, how about together tomorrow morning? User says, sure, would be great with your recommendation. And machine says, really? I mean, so it's not able to follow through in this interaction what's happening in terms of, we're talking about breakfast, and instead of responding to that, it kind of just goes on a different tangent about how about tomorrow morning, and right. So there are issues with there are lots of issues. Open-ended chat is hard because there are lots of possibility at a given point, and so you have to be able to do a lot of things. Unlike the task-oriented chat engines where you are following through, you have a goal in mind. Here, there may not be a goal. So having an open-ended conversation is really hard. But we'll talk about how some of these things done, especially things like ChatGPT. As we see these things, right, we saw in the previous case that there are these issues. And so these are some anecdotes. But how do we really systematically evaluate this? And so, excuse me, there are ways to do that, mostly objectively defined and subjectively. And it's okay if you can't read all of this, but as you can imagine, you can have subjective evaluation. So similar to what we were doing, we look at the conversation, and if I show you that conversation and ask you, okay, well, is this adequate? Is this a complete conversation? Is it friendly enough? Is it fluent enough, right? Is it helpful, and so on? So this set of methods essentially require human judgment. We typically, at least in my experience, my group has done these kind of experiments using crowdsourced data. So you essentially provide snippets of conversations or sort of segments of conversations to a Mechanical Turk worker or some other crowdsourced platform, and ask them to rate things along different dimensions like adequacy, fluency, coherence, variation, friendliness, and so on. Okay. It is, of course, tricky because when you present something to a user and saying that we generated this, what do you think? Do you like it? Most people say, yeah, that looks good. That's nice. And so you have to be careful how you phrase this. People are nice, so they want to be nice to you. And so if you end up asking them questions like, do I look good in this shirt? I mean, they're going to say yes, right? So the better way to ask is, okay, I have these two shirts. Which one is better? Which one looks good, right? And so that's a different phrase. So often in this case, we would have things generated, say, from a baseline, and we would have things generated from some model. And then we ask the users to compare them and do the relative rating as opposed to, do you like this? So you have to be careful about how you phrase. Otherwise, you may end up getting kind of assessment that's not actually faithful. And then, of course, there are objective assessment where you don't have that problem, right? So you don't have the subjectivity issue. And there are several famous popular methods like Blue, Meteor, Rogue. And these things, the good thing about them is you don't have to do the expensive user studies or human judgments or crowdsourcing experiments. You don't have to worry about the subjectivity that may be there, but it may also not give you a full picture. In fact, many times we've found that there's a big gap between what you find through subjective and what you find through objective measurements. often there's a negative correlation. And that's kind of really hard to then explain why that's happening, right? So one thing we would recommend is you should always think about some kind of real user trial, because a lot of things that we are able to measure more easily through objective measurements may not actually map to a good or better user experience. So at the end of the day, given that we are interested in creating some experiences for the end users, what matters is how they perceive it, as opposed to what we can measure through our measurements. So again, you have to be, evaluation is a huge deal. And, this is, I mean, in a way, this is true throughout information retrieval. But here, given that we are dealing with natural language interactions and direct implications on user experience, maybe it becomes even more important. Okay, so this kind of gives you a little bit of overview of what we're going to cover in more details in the coming segments. But before we start wrapping up this segment, I want to mention a couple of this new trends, right? So as I said, between us submitting the proposal and coming here, there's a lot of things happen. The biggest thing, the elephant in the room is ChatGPT, of course, and unless you are living under a rock, you probably know what ChatGPT is. It's based on OpenAI's GPT 3.5, which GPT stands for Generative Pre-trained Transformers. And these GPTs, they're trained, they're built using large language models, which is they're trained on large corpora, mostly from English Wikipedia, PubMed, and many other corpora that are available. If you're interested, and if you didn't know this before, GPT-2 is actually available free, open source, so you can actually play with it, you can work with it. OpenAI also has APIs available with some limited access, so you could also use GPT-3. And then there are other tools, there are other APIs that are emerging. So if anyone is interested, there are tons of resources now being available. Some of them are free, some have some minimal costs because these things are expensive to run. ChatGPT ended up becoming increasingly popular it was launched at the end of November, but by January, it already had passed 100 million users. For reference, it took TikTok 3 times as long to get to that number of users. If you think about it, like compare this to TikTok, I mean, TikTok has so much fun stuff, right? What is fun about ChatGPT? But still, it ended up getting so much attention, so much usage that it's 3 times as popular as TikTok. Go figure. Who would have thought about it? We certainly didn't think about it when we thought about this tutorial. There are lots of things happening with it right now. Of course, there are lots of issues with it. I've personally talked a lot about it, mostly in the popular press and mostly through media coverage. But there are all kinds of speculations with it. There are all kinds of jailbreaking people are doing, looking at cases where it does horribly wrong. And I'm sure you've seen it if you're on Twitter and other places. There are lots of issues, but we won't go into that. Some of those issues, I think they're kind of a little bit out of our focus here today about how they have led to some layoffs and so on. But it's important to point out that not long ago, Google, in response to this, released Bard, which is Google already had their system called Lambda that they demonstrated about a year and a half ago, about 2 years ago. And they've been working on it, but in response to OpenAI's ChatGPT, and Microsoft has exclusive license with that, and they've invested in OpenAI. So that means ChatGPT is really associated with Microsoft now. So in response to that, Google released Bard, and then the next day, Microsoft announced, which was, we knew it was coming, but we didn't know it would be coming so fast, is ChatGPT will be integrated in Bing, what they call New Bing. And you can see this was less than a month ago. So we are, I don't know how many other tutorials can claim this, but we are really talking about things that are happening just a few days before. And we are, we're bringing this to you because it's that relevant. So today also we'll be talking a little bit about how ChatGPT works and some other, architectures with that, how it impacts the work we are doing now, we're going to do in the future. Those who are interested in this field, it's rapidly changing. Okay. So we are here at this point to do a couple of things. I want to do a little bit of like this exercise, and we haven't tested this, so we'll see how it goes. But we have some people here and some people online. So we're going to ask you to play a user agent kind of a role. And so if we can have people pair up, and one of you will act as a user, other will act as an agent. And we have some instructions for you, right? Can we do that? This is a tutorial, this is a class. So we want to make it interactive. All right, so here's, you can just give it. You can copy the instructions from the slides, like it's in the notes. No, it's actually, it's in the slide notes. So if you can, and Grace, you want to give this to one pair? No, only one person in the pair will get. So this is the instruction for the one who's acting as a user, and they have to hide this from the agent. Okay. So it's a task we are giving you. So identify which one will act as a user. Okay, or you can be in a group of 3. That's fine too, I think. But only one person will be the user. So the user gets to see the task, and they will use the agent to solve that task, right? So the agent doesn't get to see what the task is, but they will only get to respond to what the. So here's a kind of instruction. So we're going to create the pairs. The user is given a task. Don't reveal it to the agent. The user starts asking questions to the agent to fulfill that task. The agent, so this is those who are acting as the agent, they can do web search, or they can just go to some website or whatever, and then answer that question. But you can't, so you have to be like really a robot. I mean, not a good kind of robot, but bad kind of robot, right? So very robotic, very mechanical. You cannot use your human side here, right? So no, subjective assessment. Multi-agent. So agent can only provide what they actually find online. So they cannot provide their own knowledge, assessment, or whatever. Like, so of course you're all humans, you might know things, but you can only provide the answer that you can actually find, you can actually point to online. Okay. And you have to do this in 30 seconds. So once the user gives you something, tell them something in 30 seconds that you can, including, I don't know, right? But that's it. That's the extent of it. You cannot modify the user request. You cannot extrapolate it or extend it. You only have to respond to what the user said. The user can give a natural language question. So the users, those who are acting users, you don't need to throw keywords. You can actually have a question, right? But that's all the agent is meant to respond. And again, 30, I mean, we're not keeping timers, but like you have to, like, you can't take forever. So agents, you're not going to go out, like do some research. You're going to quickly look up and respond within 30 seconds. Okay. So we're going to spend no more than 5 minutes to do this, which means at the most you get like maybe 6 to 8 turns. Okay. All right, let's start. And then we'll talk about how it went. Okay, guys, we're gonna come back, and wherever we are, we'll just see where we got to. Okay, so just to reveal, in case the agent didn't get, this is a travel planning task. I mean, if you didn't get this by now, you're way off. So I don't know what we were talking about, but this was a travel planning task. So let's hear, like, users, did you get your task done? Yeah, like, let's just.
Hi everyone, I'm Abel. So I'm from NUS. So in my experience, I think my AI is quite good in its response. Like, yeah, my AI. Yeah, I mean my AI.
Okay, I'm Zhipeng from SMU. Yeah.
Yeah, but although like it's a human, so after all, so it would take a while to go online and search for the answer. But yeah.
No. Yeah, no.
All right. Were you able to do that in like that 30 seconds, 30 times?
No. Yeah, so most of the time I just answer I don't know. Yes, from a AI prospect, yeah, not a human prospect.
What did you do when got the I don't know? You then revise the question? Did you do more research? What was the
I did try to clarify my query, right? So to ensure that my bot can understand.
Thank you. Let's hear from other people.
Hi, I'm Nibobo. I'm a visiting student in AUS.
I'm Jiapeng. I'm from SMU.
I plan to go to the Thailand, and I asked my bot to search the ticket accommodation and the most popular food for me, and he gave us some recommendation, and I think he's very okay because he gave he recommendation he give the 5-star hotel, and I plan to go there.
Yeah, hi, my name is Samarth and I work at DBS Bank. So yeah, so I started with asking a high level question that I want to plan a trip and all that. So I have 2 agents, so lucky me. Yeah, they started with some clarifying questions on like where they want to go and things like that. Then they gave me some recommendation. Then I added more constraints to it. That okay, I want a family trip. We are 3 people. Then they revised their recommendation. And also provided some quotes. Then I also asked them more about the travel options and things like that. Then the agent provided me more information around those lines. So our approach was more like provide a recommendation, ask more clarifying, more questions, or add more constraints. Then my agent revised their recommendations. Yeah.
Hi, I'm Seonyang Park from Republic of Korea. So I'm a student at Seongnam University and also working at a company called NCSoft. And as I try to answer the questions, the queries, I found it difficult to answer within 30 seconds because he was adding some constraints and he asked like is the flights included? And I was like, Not sure. And I had to read it back again, the blog posts and all that. So it was a bit hard for me to act like a smart conversational agent.
Okay, another boat is from Beijing, China. Okay, I'm the visiting scholar in NUS this time, and I find it is very hard task for me because I'm new here in Singapore. I don't know many things about this city, so he asked something about around Singapore. Um, the city around the country around Singapore. So it's very difficult. So I direct ask the ChatGPT about this, but it provide many information, so many information. So I too much to reply to the to my agent. Yes. Thank you. Use some item because it lists many things about 8 suggestions. I will not be at that time. Yes.
Okay, thank you. So you kind of cheated because we didn't expect somebody will use ChatGPT or so. But that's fine. Thank you all for participating in this. Unfortunately, we couldn't do the same for online users. So, but hopefully, they have the task instructions that they can at least follow through this discussion. The thing, we wanted to really constrain you to just a web search and any direct thing that you can get. So let's say, you know some travel website or some travel blog that you're already familiar with. You can go there and look something up. Essentially, you're for the agent, we're trying to really mimic a typical agent, what they would do currently, right? Not ChatGPT and not other things that we're going to talk about, right? The things that would introduce some proactiveness. And what I mean by proactiveness, and that's sort of the next thing we're going to, talk about quickly, is proactiveness we define by the agent introducing new things in the conversation. So whether it's a new intent, new value, or new slots, right? So we took that example of find me a Chinese restaurant, and we saw how we can respond to that. But what if you also introduce these other things in that, including, even though you're looking for Chinese food, I know this Asian fusion place, that's really great. And I mean, they have Chinese, but they also have Korean and Malaysian and other kind of things, right? And yeah, it's a little bit of walk, but it's worth it. So humans will do that. So even though you ask me for a good Chinese restaurant, and maybe you meant like somewhere close by, I'll say, you'll have to go a little bit further for this, but it's worth it. It's really great. And it's not exactly Chinese, but you got to try this. So what's happening here is the respondent is being proactive. I'm actually going above and beyond what the user, you specifically asked for, right? And so here's an example. But there are a lot of these kind of examples where the agent can introduce new kinds of things, right? One of the examples that I've often given is when the user says, I want to go out running, do I need a mask? And the agent will, in response, say, well, if you're looking for something to do outdoors, maybe you can go biking and you don't need a mask for that, but make sure you have some water because, it's a little hot and you might get dehydrated. So in this example, what's happening is agent is not simply responding to that question, original question, like if I want to go out running, do I need a mask? Sure. I mean, the agent can respond to that. Well, maybe, but it identifies that what the user is looking for doing here is some outdoor activity, right? So that's one thing. So the agent suggests, how about biking, right? And the second thing, agent realizes that the user is concerned about safety or health because they're asking for mask. And so then the agent says, well, biking, you wouldn't need mask, but make sure you take water. So the user didn't ask for this, but the agent is being proactive. So there are a number of ways one can be proactive. Humans are really good about this, right? Here's an example, and again, there are many of these examples. But what happens typically with these kind of proactiveness is the agent can often ask for clarifying question. What do you mean by this? Or would you also care about this? So that restaurant example, right? That you're looking for somewhere close by. Are you okay for like some fusion restaurant instead of just Chinese? Right? I mean, what is your level of comfort with these kind of things? It could not only just answer the questions, but also suggest better questions to ask. Once again, humans are really good with this, right? And if you are in an academic setting, you have a mentor or advisor, this experience where often your advisor or mentor is there not just to answer your questions, but also encourage you to ask better questions. Right? So your interaction with that mentor often includes this proactiveness from them. Right? And other thing that happens is topic shifting. So this is where the agent may seem like going off the rail, that they're, instead of just answering the question, and kind of going to a different path. But that's actually an important thing. That's a desired thing. So that example I gave where the user is asking for running outside and the agent ends up recommending biking, that's an example of topic shifting, but it's done with an intent to give user a better choice, because often users don't know what are the possibilities. So if the agent is smart enough, is proactive enough, would then provide these kind of suggestions that the user hasn't thought about. Right? Again, a good teacher, a good mentor, a good friend would do these kind of things. They would not just blindly respond to your questions, but also make these proactive suggestions that agents can do. Right? How do we know that this is actually working? How will the agent know that the user needs something proactive like that, or that this kind of thing is actually working? And there are different ways the agent can figure out. One simple way is just agent can ask, like, did I answer your question? Does that help you? Right? And the user can, yes. So that's a clear way. Other things, implicit feedback, right? So if the agent starts saying something, the user says, no, I don't care about that. So that's a feedback. That's an implicit feedback. That means, what the agent was providing is not helpful. It needs to change something. And other times there is this kind of unsolicited feedback. So agent is not even asking, but if the user says, oh, that's a good idea, or thank you, right? So again, that's a way for the agent to know, okay, well, that was a good, response. So there are different ways this could be evaluated, because here's the thing, when we go on this proactive route, the challenge is now it's no longer straightforward to assess relevance. So we all understand relevance in a typical information retrieval sense, where the response needs to be on the topic of the user's query or question. But now when the agent gives a different kind of response, you can't simply say, oh, is it relevant to that topic? It may not be direct relevance, but it may be relevant to accomplish some goal. It may still be useful to the user. It may still help advance their goal. So there are different ways we need to think about for evaluating this proactiveness thing. All right, so with that, we're gonna actually take a break here because it's coffee time. But as we go forward, we'll now talk about, okay, how do we actually do this? What are some of the specific techniques to bring in proactiveness? How do we evaluate it? How do you work with it? So that's the kind of thing we're gonna cover. But now it's time for coffee. So see you back here in a few minutes.
Okay, let's start the second part, and we will go through a set of topics, such as you see the proactive ontology expansion and also learning to ask and the topic shifting. I will go through those two first. So the first one, for proactive ontology expansion, we separate those to two parts. One is a new intent discovery. So whether the user utters some new intents or not. And then also new slot induction. And regarding the new intent discovery, we first give some definition, give some examples. And then we have two scenarios. One is discover from scratch, which means we don't have any label data yet. And then we want to directly observe from the conversation and find out those intent classes. And then another thing is we discover some new intents from data. In this scenario, we have some labeled data, which have some intents, but also we have some new intents. This one is more kind of realistic when we have already get a conversational agent, and then we deploy as a real system. But sometimes new scenarios or new things might happen, right? And then in order to update this kind of conversational agents, we need to discover some new intents further. And then after that, we will introduce some new slot induction. So this one is a little bit of similar, but also different. We will give an example to show you what is the difference. And then we will give some traditional approaches and also introduce some emerging methods. So this is for the ontology expansion. First of all, what is intent discovery? Basically, it wants to uncover some novel intent categories. So maybe we start from scratch, or maybe we have existing one and we just want to focus on those new ones. And it is actually very critical for the development of practical conversational dialogue systems. So here we give example like maybe we observe some like a multi-turn QA or dialogues. And then we want to kind of transform those kind of utterances into some intents that is expressed here, such as I forgot my password. So this one is kind of password forgotten intent, right? We want the agent to take some action. And then maybe I lost my credit card, right? And then this one is kind of report lost the card, this kind of intention. And given the intention, then the agent can reply, right? Do you want to be suspended first? Or say, no worries, I can help you to reset it. So those are the kind of expected responses we want the bot reply us, right? So in order to give this kind of responses, the agents need to, first of all, understand the correct intent here. So this is the intent detection. And then we have some existing methods for discover intents from scratch, which means we can observe a lot of conversation data, but we don't have some labeled intents yet. So how do people do this? Basically, it will go through those labeled data, right? This is a pipeline. Usually some early works do in this kind of series. So they will first do feature extraction. So a lot of features can be constructed here, like some keywords, right? Like post of, POS tag, or like word embedding some topics here. So they extract a lot of features. Most of them are actually some manual features. And then they kind of doing some auto encoder or just some different kinds of encoders to encode the input and then do some kind of feature assembly. So suppose we have a lot of features, we kind of assemble them together. And the important thing here is do some clustering. So because each sentence, we will map it into like a feature vector, right? And then we want to use the feature vector or the feature representation of the utterances to do clustering. And then cluster out several, groups. And then we will assign, we will kind of use the cluster, maybe we directly as the label, or maybe we can use this as heuristics for annotators to get a faster annotation. So this is the way when we do intent clustering, intent detection just from scratch. So this step actually can be very useful when we want to build up conversational agents from the very beginning, right? We want to get those labels. But this kind of methods actually also have some shortages. For example, it relies heavily on some manually designed features, right? This one is hard. And also, In order to train a proper encoder or say feature extractor, we usually need large data sets to train a very good network parameters. So this one is also one of the shortage. Another thing important here is because we are doing clustering. So it is very hard to produce intents in like different granularities, right? Sometimes it's very hard to control. So we also have another scenario, which is a lot of people are actually doing this. Instead of doing it from scratch, sometimes we will give some labeled data and then let the model to find the new kind of intents, right? Something like this. Suppose we have some labeled data with those observed intents, which means the label we already know. And then we might also have some unobserved intents in the data, right? Such as, can you help me link this card to my Google Pay, right? This might be an intent not inside the non-observed intents. Then actually a lot of research works are doing this. So they want to kind of use the unknown data and help the model to kind of detect the unknown intents. And for this kind of scenario is actually very realistic. And it is a very realistic during the system deployment. So how to make use of this kind of known data to help us to find the unknown? A lot of people are doing semi-supervised learning or say semi-supervised clustering. So how to do this? There actually are two essential questions. First is how to better cluster the utterances, right? Formerly, when we are discover the intents from scratch, we are also do clustering. But here, where we have some labeled data, how do we make use of those labeled data help us to do kind of better clustering, right? So this is the first question. Another question is, before we just use an autoencoder or say any kind of encoder to get a feature, now is how to learn some semantic utterance representations to provide proper cues for the clustering. So which means how do we represent the data in order to get a better clustering performance? So those are the two essential questions we need to answer. We answer them one by one. So firstly, how about the clustering process? For the question one, a lot of mechanisms actually are proposed. The first one is we can use constrained adaptive clustering. So what does this mean? Suppose now we have a set of data with label and also a set of data without a label. It will, so here is how they do here. This is the encoder, right? At this time, 2020, already transformer is already very popular. So this one makes the transformer network to encode the utterance and get a feature. So basically we can think, suppose we have an utterance, some are labeled, some are not labeled, right? It doesn't matter. We just get utterances here to encode it. When we encode the utterance, then we can get some kind of representation, right, for the utterance. And then we will map it. Here is extract the intent representation. So here, suppose we have a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5 utterance. Suppose, I just give an example. Suppose we have 5 utterances. We will extract a representation for each utterance. And then the next thing is, we will compare the similarity among those 5 representations, get a similarity matrix here, right? This is 5 utterance, we get a similarity matrix. And because now we have some utterance we know the intent, some of the utterance we don't know the intent, right? So this is how we do, we make use of the label data. We have a similarity matrix here. And because some of the data we know, suppose those 2 utterances, we know the label, then we can directly calculate the similarity matrix, right? And this matrix is based on some label data. Some unknown data, we just leave it as a blank. So this part is the label we have. This one is the real similarity matrix extracted from some feature extractors. And then we make use of this and this to propagate the label to those unknown data. So suppose we have a labeled similarity matrix here. We got the matrix by calculated from here, and then we compare those two, and we can use those two to get some threshold. Suppose some are similar, right? In the same intent class, they should be similar. In different intent classes, they should be dissimilar, right? So here we can, based on this information, get some dynamic threshold here, and then use this kind of thresholds to propagate the label to some other unlabeled instances. So you see, those are the constraints here. So it's the similarity constraint and the propagate from the label data to those unlabeled data. So in this work, this is the general kind of pipeline, is how they make use of the labeled data. They just use the similarity and get a threshold and propagate to others. So in this kind of process, actually they have some shortages. Later we will show. So this is, for example, if we only care about the pairwise the relationship, sometimes it's only getting the similarity between two instances, right? Sometimes the cluster information actually, the global view is kind of less focused. So there is another improvement from the same group of people. So this is the process. Yeah, they are using the BERT. So this is the same group of people do a further improvement to get a kind of a more global view. So how did they do? This one, again, they are still relying on the transformer to do the feature extraction. And they will obtain some pseudo supervised signals using k-means. What does this mean? I give you an example here. Suppose this is the whole data. And this one, those colored ones are labeled data, right? For example, this one, the blue circle is one intent. This brown rectangle is another intent. And then those triangles, we are not know yet. So it's unknown intents. So suppose we have those three samples labeled, we can still make use of those label data to train the classifier. So this one is okay. We kind of use the label data to train the transformer and then use it as a feature extractor. And then use this to extract a feature for all those samples, the labeled one and unlabeled one. So we can both extract the feature. And then suppose now everything is in the feature vector, right? And then we can do some kind of a prediction. We predict the number of clusters using those features. Suppose given all those features, we can predict that we have 3 clusters. So we use the 3, which is the k number, and then we can do k-means directly over those feature vectors. So now we will have 3 clusters. But remember, because those are directly applied the k-means and give the result, which might not be true, right? So we call this as pseudo labels. And then now in this turn, we will have kind of global view over all the data, right? So it's because we are applying the k-means, get all the labels. But sometimes it is not so sure. It's just using the training data of those 3, right? Train the feature extractor. And then we now get the cluster assignments. Now the important thing is this, alignment. So suppose now I get 3 clusters, we will get this vector assignment for each cluster. And we will further use those data to train this model. Suppose now I have 3 clusters, all the sample we will have pseudo label, and then we use the pseudo label to train the model. And after we train the model, we can again extract feature for those, right? Because now this model is kind of updated. It consider all the information from the k-means, get a kind of overview of the data. And then we train this model again. Train this model again, we also get the feature vector. It's kind of updated feature vector. And then again, we do the kind of clustering. So we can do this loop again and again and again. But one problem is, the first time I do the clustering, we have 3 clusters. Next time I do the clustering again, maybe we also get the 3 clusters, but the cluster, how do we align them? Sometimes the label of the label of those samples might shift a bit, right? So this is why they do this kind of cluster alignment. So this is to ensure that in the first epoch, I train the parameters. The second epoch, I train the parameters again, those are kind of a gradually change. It helps to align the labels like this one is in this cluster. Next time, it should still be in the same cluster. So by doing this kind of alignment, we will kind of making this thing run and run until the converge. So this is how this model improves over the former one. Because the former one, we only care about the pairwise similarity, but now we are working on the cluster level transformation. So actually this one works better than the former one. And the alignment part is very critical. If we disable this, then the thing will not work. So we actually try this, and the alignment part is very important. So this is about the clustering part. The next question is how to learn semantic utterance representations, right? This one, the former two works actually already use BERT, like use transformers, but actually we have more advanced versions. So for example, this one. How about we directly apply vanilla pre-trained language model? This is doable, right? We can directly apply like a BERT, like other transformer models to extract feature for those utterances, but it might give us like a worse performance. It's not so good. And then another thing is that we can use those some labeled utterances because we have some data with label. So we can use those labeled utterances of those non-intents to train the encoder further. But this one also have some shortage, right? Like the former two works, they're all doing this way, right? They use the label data to further train the encoder, but it needs a lot of samples to do this, right? In order to train the model properly. And also sometimes if we have if we emphasize on the label data too much, it might let the model becomes a little bit biased, right? So this is another question might encounter. So in this paper, actually the authors introduce a multitask pre-training using some external data and also the in-domain data, which is the real data they focus on. So this one helps the model to kind of learning better. So how did they do? They still use the BERT, but do the pre-training or training in 2 stages. The first stage, they do pre-training. So it's kind of, they make use of some public intent data set. So these ones are some like set alarm, play music, calendar. So those intents might not be exactly as those in-domain data, but anyway, those can be useful. So they make use of those data. And then for the in-domain data, remember, we have some labeled parts, right? We also have some unlabeled data. So they will treat those data separately. So for example, for those public intent data sets, they have label, right? They can use cross entropy loss to train it. Sorry. And then for those labeled non-data in domain, they also can do cross entropy loss, right? They have the label. And then for those without label, they use max language modeling to further tune the BERT. So this is how they do the pre-training. After do the pre-training, right? The kind of already at a kind of a good stage, they further do contrastive learning. How did they do? They will apply contrastive learning with nearest neighbors. What does this mean? I give you an example. Suppose here, right? X1, X2, X3, X4. We give 4 labeled data. And then how to make use of it? Suppose now we already pre-trained the model, right? So we give an utterance, it can extract the feature back. So how do they do? We will use the model here to extract feature for all the sample. And then we calculate some neighbors. Like X1, we give a set of neighbors for it, which is N1. And the X2, we also calculate the set of neighbors, N2. And the X3, X4. So each utterance, each labeled utterance is paired with a set of neighbors. And use those, we can do the contrastive learning. How did they do? Before we do contrastive learning, usually is a similar utterance will be bring together and the different ones we will push away, right? So this is the kind of contrastive learning what we do. And here is, we will bring together those nearest neighbors similar neighbors together. So here, for example, the original one is X1, we will bring with those green rectangles, right? Be together. And those for the X2, for this one, we will bring together those yellow triangles. And then in this one, because you see the X2 is inside the neighbor set of X1. So we will treat all the neighbors of X2 also as positive samples of X1. So this is the difference in this paper. How did they do? They kind of use the neighbor set to kind of affect the real positive samples. So you see here, given the X1, this X2 here will be a positive sample for it. And his neighbors, his real neighbors in the green circle is also his positive ones. And the ones inside the neighbor of X2 is also treated as a positive samples for this X1. So this is the difference from existing contrastive learning algorithms, and all the others are negative samples. So you see, in this paper, they do this kind of pre-training and neighbor-based contrastive learning, and they achieve kind of better results, like in 2021. And also, they are, in order to get a better representation, there are more works. In this work, they're trying to use aligned knowledge transfer. So how does this mean? Before, the existing methods I introduced to you is more like they have a pre-training stage, right? They use the labeled data, which is the in domain. This IND means in domain. So those labeled data to train the model, right? Train the model first. And then for those out of domain, which is the unknown data, unlabeled data, they will also use the trained model to extract features and then do clustering and then get the labels. They usually form this kind of pipeline, right? As all the methods I introduced. However, because the in domain and out of domain, the model actually is treated as two stage. One is training the the feature extractor, usually using some cross entropy loss, blah, blah, like train as a classification task. And then for the out of domain data, they're doing like clustering. So classification and clustering is treated as two stage. And the losses actually are also different. So they have some discrepancy. So in this paper, what they do is they equip the traditional pre-training stage and the clustering stage with the similar contrastive objective. So it's kind of they're making the loss, kind of combine them together. So making the pre-training stage and the clustering stage with the same kind of loss. So how did they do? Again, all the utterances, like no matter it is in domain, which is with label, or out of domain, which is without label, right? They're all making those utterances into the BERT, do some intent representation, which means becomes a vector here, right? And then they have two kinds of head. One is on the instance level, another is in the cluster level. And then if it is the pre-training part, which is the green, right? Green stream. For the instance level, they do supervised contrastive learning, right? With the label. And then in cluster level, they use cross entropy, which is the real intent label of those cases. So you see, is inside here. And then when it is in the clustering stage, it's similar. This one is still use instance level contrastive learning. And then in this one is using the cluster level contrastive learning. So it's kind of making the two stage go through the same pipeline and with the similar losses. So this is the improvement over the former kinds of two-stage methods. And also we have more. So in order to improve the representation, there is another work using graph neural networks. How, at the first sight, you might think, how does this graph neural network might work in improving the representation? So here, we actually is a specific scenario, right? So this one is focusing on discovering some new consumption intents, which is crucial for some downstream applications. So basically, the idea is that is because user consumption usually is not only determined by users' intrinsic preference, like a brand, like price, blah blah blah. Yeah. So usually also those, the consumption of a human also largely affected by some spatial and temporal factors, right? Like for example, this user here in some shop, right? And then at night, right? And then is eating some hot pot. So this one is kind of gathering with friends or gathering with family members, right? This kind of intent. And then suppose there is a user at home and it's a morning time and it's looking at some like kind of vegetable things, right? This one is usually as cooking at home, this kind of intent. So we see the user with location and the time, right? Temporal factors, those things also affect us when we decide what is the intent. So here, what does this work do is they construct 3 groups of dual hypergraphs to capture the relations and the aspects. For example, the user, right? And also the look. This one is several kinds of actions, right? Each is a kind of an action, and each action is regarding a specific user at a specific location on a specific time regarding a specific category of items, for example. And then they construct this kind of a graph, like user versus a location, they give a graph. User versus a time, the temporal factor, right, give a graph. And the user with items, we have a kind of graph. So usually in e-commerce websites, we only care about the user and the category thing, right? But here they have more, user together with location, user together with time. So we actually have a lot of examples here, right? Suppose the user may have some for example, the user may have here, like in the noontime, right? At office, like in some office buildings, usually user might tend to consume some quick food, right? Like in office hours. And also at night, in some like a cinema, then it's more like consume like some watching some movie or like in some bar with friends. And then if it's at home in the morning, then it's more like having breakfast, blah, blah. So those kind of intent is closely related to those spatial and also temporal factors. And in this work, they use hyper neural networks to extract those disentangled intent features from each of those graphs. And then they will apply kind of hypergraph neural networks to extract the features and then integrate them together, right? This is the location aspect, the time aspect, category aspect, and then use attentive fusion and then later decode the final intent. But the important thing here is they model those behaviors in different aspects and then integrate them together to get a more accurate intent prediction. So this is another thing about how to learn better representation, right? Okay, so those are for those new intent learning or discovery, but still we have open problems. For example, those directions have already, I seldom, I didn't find the kind of work that is focusing on those kind of tasks, but it's also very important in real applications. For example, about the early detection of new intents. Existing works kind of focusing on some public data sets, right? But in real life, actually some importance, some of the important issues is how to detect those intents as early as possible, right? So how many instances to signal a new intent, right? We want to discover those new intents at the very early stage in order to make it perform better or say cause less human insatisfaction, right? And also when we're looking at the data, sometimes it might not be sufficient to raise a new intent, right? how to decide the necessity of raising a new intent. So those are some open questions. Also, usually when doing kind of system maintenance, we actually have some human feedback quota. Sometimes, suppose we have this kind of limited quota that allow human to help us do some modification, how to efficiently make use of it, right? Because when we purely rely on some automatic algorithms, the result we returned by those algorithms might not be so reliable. So sometimes human feedback is really necessary, but how to make use of those human feedback and effectively make use of it is a critical problem. And I see some work is using active learning, combined with active learning to do it, but I mean, it is still in some early stage. And also how to refine the intents with slot structure. This one is, I think, is also a very important aspect, but less people are doing this. Because remember in our example, usually we have an intent, right? And together with some slots, and we require the value from that. But actually the intent classes and the slot structure are closely related. Those two things, I mean, the slot in the discovery and the slot discovery and the intent discovery actually is very closely related. Currently, people are doing it as separate tasks, but how to balance between them is also an important issue. And of course, there are more. So I just list them here. So now we go into the new slot induction. So the slots. And I will give some definitions, some traditional approaches, and also brief introduce you some current very popular or say famous methods. So first of all, regarding the new slots, we first look at the slot filling. So slot filling is usually identify some word span, or we generate, predict some values based on the given slot from an utterance. So this one usually is used to represent the meaning of the user. For example, like this one, like I would like a moderately priced restaurant in the north part of the town. So in this utterance, usually when we usually the current slot filling techniques, the slots actually are given. So it's kind of, we can treat it as a QA task, right? Given the context, I give you a query price range. Then you predict the moderately priced this value for me, right? Also, I give you the query area, and then I give you the utterance. Then you predict the north for me, right? It's like a QA task. Give you the context, I give you the query, you return me the answer. Whether it is predicted one or extracted one, it's okay, it doesn't matter. So this is how the slot filling currently doing. And all this actually assume the slot, or sometimes we call it slot types. So those slots are kind of known, but it might not be true, right? Sometimes in the conversation, we might not know the slot yet. So this is the task of slot discovery. So for new slot discovery, it is sometimes if we only care about the new slots, it usually emerge after the deployment of the system, right? Rendering some supervised methods ineffective. So before do slot filling, we're using some supervised methods. But here, suppose we have some new slots, then the existing one will fail. So suppose here, suppose we have a conversational agent for restaurant booking. So usually we might already develop the system, right? We have some non-slots like the price range, which take the value expensive, moderate priced, or cheap. Or we have another slot like area, which take the value from like east, north, west, south, center, blah, blah. So suppose we have an agent like this, and we have the ontology, which is the slots and what the value it can take. But after we deploy this system, some new situations might come. For example, the COVID-19 in 2019, right? Suddenly, when we booking restaurants, people will ask some question about vaccination, about how many doses you have. Then in this kind of scenario, how the existing chatbot can handle, right? So this is why we need some new slot discovery, such as I have taken 3 vaccination doses. Will it be okay? Actually, the user are giving some information about vaccination doses, right? Which can take a value like 0, 1, 2, 3, 4 or more. Right? So those are some new slots. And also, the user might reply that we are fully vaccinated. So this one is telling us that the vaccination status, right? So they can take a value of vaccinated, in progress, not vaccinated, or unknown. So this is why this kind of new slot discovery is important. Suppose we don't know the slots, then the agent might fail very easily. And how do we do this? Actually, there are many works in early years, like 2014, 2015. So they do this automatically. So which means, for example, there are two methods here, but I just show the common thing inside. So basically, they will have an unlabeled collection. So again, it's a set of utterances and with no label yet. So they will do some slot induction by some tools. So what does it mean, tools? Usually some NLP tools, such as frame, semantic parsing, or some syntactic dependency parsing. So this kind of tools to extract certain span and with some labels on that. But this label is not a slot label. It's actually some like a semantic parsing label or syntactic label. But anyway, those things still can be used. And then given those, they will select some slot candidates using some like a semantic knowledge graph, and then do a bit of ranking, right? Based on some features, they do the ranking and manually select out those candidate slots and the mapping to some names. And similarly like this, right? They can use some name entity recognition tools or some frame parser, right? Like this, find a Chinese restaurant that's cheap. Then they can do some kind of frame parser. We are kind of given this value and give a label like origin. So this is kind of label in those parsers. And then like a restaurant, which is locale, this kind of a label. And then cheap is expensiveness. This is the label also in semantic parser. So they will use those existing tools to pass those utterances and give some span together with the labels. And then further make use of those things like emerging and the selection. So some of those kind of labels can be merged together, and some of the candidate values also can be merged together, and then do selection as a kind of a loop. So this one is similar as this. And then later give the label and then train on some label. After selection, they have the label and also some value, right? So they treat this as a labeled corpus and further train the tiger and then get all the things. So basically the common thing here is this part, right? A lot of manual selection, manual merging, this kind of process are there. So this is kind of shortage of these methods, right? The manual process needs human intervention and largely affects the final results. So how did they rank? How did they select the merging will directly affect the final output. And also, this kind of methods actually works on some corpus without any slot labels. So those kind of automatic thing actually works from work from scratch. So usually we might also have access to a small amount of label data in real practice. So now we will introduce how do we do in this kind of scenario. So again, we have some label data and we also want to find some new slots. How do we do? Suppose we already have some label data, right? Labeled slots and some value. How do we find those new ones? A popular way is do some cross-domain adaptation. So how do we do this? Actually have one stage, also have some methods working on multiple stages. We first introduce the one stage thing. So here we will have some source domain. So which means those samples with labels. And also we have a target domain, which is some samples, but we don't have the label yet. Actually, yeah, you see a lot of methods actually in recent years working on this problem. And this one, this framework actually is just from this paper, but I think this one is very representative, so I show here. Many of the works assume that for those unlabeled data, although we don't know the slots, but they know how many new slots they have, and assume they know the description of those slots. So you see it's a little bit of unreal, right? But those works have this kind of assumption. So suppose we know how many new slots we have, we know how many slots, what are the descriptions of those slots. Some of them even know some example values. So this is the method that with slot description and also the value. So suppose I'm talking about those methods without the example value, then you can ignore this part and directly just see this part. So for those kind of methods, basically it is a sequence labeling task. You see, for example, the utterance is play, imagine on Pandora. This is the input. It will directly encode it into some vectors. This one is use GRU, bidirectional RN, etc. We can also use like BERT. We can also use other transformer models. It's okay. So the basic idea here is, given the utterance, we encode into vectors. And then we also encode the slot description for those new slots. Then we kind of use this attend to the word representation of each token. And then we do a sequence labeling. You see, we have four words here. We have 4 vectors here. This slot description will attend to each of them. And then after the integration, we predict the beginning, out of scope, or inside the BIO. And then we get the final label. So basically it's a sequence labeling task. So here, the difference, if we have some example values, then this example values is further encoded also, and then attend to all the words inside the utterance. So this is the basic cross-domain adaptation kind of work. It's basically they treat it as a sequence labeling task. And each word encoded and then use the slot description, attend to it, and then finally predict the final result. So this is how they do. We also have 2 stages. This thing, again, right? This thing is a little bit different from the other thing. Remember, for the first one, right? They just input the whole sentence and directly output the label, right? The label of each word. In this one, it's a little bit advanced. They give the input of the utterance and then firstly predict the BIO. So it's kind of the extract of possible value first. So here, suppose play Portsmouth by Paul Smith on Google Music. They will extract those kind of name entity first, like Portsmouth, Paul Smith, Google Music. They will extract those values first. And then kind of classify those values into different slots. Here, again, they still have the slot description, right? They make use of slot description, map the value to the exact slot description, and then get all those new slots. So you see the slot values identified by sequence labeling first, and then do the slot type classification. Like given this Portsmouth, it will do the similarity to track, artist, service, and then finally define, oh, it is a track, right? This kind of slot. And then Paul Smith get out the information, and then again multiply with slot description of track, artist, the service, and then finally decide, oh, it should be an artist. Right? So this is how they do. The first extract the value and then map to some new slot. But anyway, they still have the slot description. So they have more details such as contrastive representation learning, right? The original sentence is like this. They do some kind of change and then get some negative representations. This one is for better representation learning. And also they can do some adversarial attack for those slot type classification, making the mapping kind of more accurate. But anyway, the general idea is still first extract the value and then map the slot, right? Yeah, so that is how the existing work. Remember, they have some shortages, of course. So for example, they pay less attention to the slot value identification, right? The value of those slots, the kind of just doing some kind of sequence labeling, right? And also rely heavily on auxiliary information. So you see, the assume the slot description is given, but most of the time when we find some new slots, we don't have the slot description, right? Suppose we already have the slot description, then why we still find those new slots? So this one is less practical. And also the fail to provide proper guidance for some cluster friendly features. They don't do clustering, right? So they of course, they don't have kind of clustering friendly features. So these are the existing problem for those existing works. We provide more. I mean, rely on those shortages. Actually, there are people further improve over it, right? For example, this one, the new novel slot detection. So without differentiation, this one also have a shortage. Later we will show. So let's look at the example first. Suppose the dialogue system, without this kind of new slot detector ability, what will happen, right? The agent said, what can I do for you? The user reply, play Is This My Words by Leonard, right? So this is the reply. And then the dialogue system try to understand the utterance of the user. Play Is This My Word by Leonard. So maybe because the system know there is a slot artist, so he can detect that Leonard is an artist. But how about this one? Is this my word? Because in the existing system, maybe it has a slot playlist, but don't have the slot album. Then it might classify this as a playlist. Then suppose the system will understand this as a playlist. After the dialogue management and the natural language generation module, it will reply an answer like this, right? You don't have a playlist called Is This My Word? Then it's a totally wrong answer, right? Actually, Is This My Word is actually an album. It's not a playlist. So this one is how, suppose they don't detect a new slot, it will cause this kind of problem. Right? Sometimes the problem can be more kind of severe instead of this. So compare again. Suppose we have a system can detect the novel slot, then it will be something like this. This one is not a playlist. Sometimes it can just say that this one, I don't know. Maybe it's a new slot. Although I don't know what the slot is yet, but I can just signal here, this one is a new slot. So this is how this kind of system doing, right? If I can detect that this is a new slot, then go to the DM and the NLG module, I can directly signal out. Is this my word? Is probably a new slot, right? A novel slot. The current system cannot handle it. So this, suppose we can signal this kind of information, it is much better than this, right? Instead of directly give you some wrong answer. So this work actually doing this, detect this kind of new slot. Because now we don't have slot description, right? The new slot description, it will detect whatever is new slot, but it doesn't differentiate what is the exact slot it is. So it's kind of advancement here. So how did they do? Actually, the method is relatively straightforward. You see again, remember, given the utterance, right, we encode it. And then we do sequence labeling to label out the slots. So for training, which is given the labeled data, right, we give the utterance, encode it, right, and then give to some softmax layer and then label it out, those in-domain slots. We can do a training like this. And then the thing is, during test, we will find some out-of-domain slots. How do they do? Go through the same encoder and then make use of some out-of-domain detection methods, or say algorithms such as a maximum softmax probability, such as a Gaussian discriminant analysis, using this kind of out-domain detection methods, and then detect out those novel slot types. It's just like, suppose we have 10 slots. Then in this method, it might output like 11 slots. We just have an extra class, capture all the new slots without differentiating what are the real slots is. So this is a kind of discover without differentiating slots. It's kind of, we have a catch up, right? Any new slot here, we just add a novel slot. Also, we have some more advanced ones, right? The formal one, because we can't detect out those new slots, but we don't know what it is. We just know that there is a new class there. Now it's kind of, we not only detect the slot, we also tell you how many new slots we have and what other slots is or are. So here again, right, in this model, it's just last year, right? We use tools to extract some candidate value first. So this one is similar to the former work. Instead of directly treated as a sequence labeling, actually sequence labeling gets some problem is because one utterance might contain several candidate values, right? Then suppose those values belong to different classes, it might give some issue. And here is, given the utterance, we first extract those candidate value first, extract out those values. And then we train the encoder with the labeled data and further tune with pseudo labels. This one is a little bit similar to the former intent classification, remember? We have pseudo labels and then use the pseudo label to further tune the encoder. So here, the whole utterance, and also we have the candidate value here, right? We encode them and do concatenate, get a feature. And because we some of the data we have label, then we can use the label to train this model, right? And then after the training, we use the encoder to extract the features for all the samples. And then we can expand the K. For example, we have 10 non-classes. And then we can use the extracted features to kind of predict how many new slots we have. So maybe like 12, then we have 2 more classes, right? So expand the K, and then again, we use clustering to clustering methods, K-means to do the clustering. And then you see, suppose those are 2 existing clusters, those 2 might be 2 new classes. And then we select out those high confidence ones. And then after we select out, we do some kind of a centroid-based self-supervision, which means this one should be similar to its own class samples and be far away from the center of the other clusters. So use this kind of loss to further fine-tune this encoder. And then we extract the feature again, and then estimate the number of clusters again, and then do K-means again, and then, yeah, so it becomes a loop. So this is why we can do kind of incremental slots. So as the process goes by, right, the K actually can be estimated directly. Okay. And then for slot detection, actually, we also have some open problems, right? Again, similar to the intent classification, how to early detect those new slots is also important. And also how to integrate some human feedback to correct those slots. And this one, right? Because slot structure sometimes can be complicated. Given a slot, we have several values. Then how to balance with existing slot structure, right? Suppose we have those slots already, whether there is a new slot, how do we define the granularity? How does it affect with the, how does it compatible with the existing slots? Those are the issues we should consider. And also, is there any better internal state representation than slots? So now everything is like slots, we take the value. However, if we want to make the chatbots more flexible, is there any new way instead of just using some slot, right? Currently, a lot of neural network just use vector representation as the internal representation, but the problem is not interpretable, it's not explainable, and less controllable. So is there any new way? So that's all for proactive ontology expansion. A lot of research work are actually still ongoing. And then we go through a bit about the learning to ask and topic shifting. So basically, you see the system, I mean, when we interact with conversational agents, actually there are some initiative involved. What does it mean, initiative? It is based on the extent to which the user is changing the conversation path. So which means who is taking control, right? Actually, we can define it as 5 levels. Suppose like I give you a question, do you like dogs? Some people just answer yes. What is your favorite animal? I'm not sure. So this is kind of the agent is taking the control, right? The user just passively answer the question. And also some lower level of initiative, like what is your favorite animal? Still reply dogs. This one, what do you like about dogs? They are friendly. Give some more information, but it's still a little bit passive. And how about the medium one? What would you like to talk about? This one say some new information. I want to talk about dogs. And then what is your favorite animal? This one say, I love dogs. I want to get a golden retriever. So this one a little bit more kind of active. And also we have higher level of initiative, like what's your favorite animal? This one say, I like dogs. What about you? So it's kind of already kind of require information from the other side, right? And also, what's your favorite animal? Dogs. Let's talk about golden retrievers. So it's kind of more active during the whole process. And then also we have abrupt kind of initiative, right? What is your favorite color? Talk to me about dogs. So this one is kind of directly shifting another thing. Sometimes it's kind of rude, right? And also like this one, what's your favorite animal? This is boring. I want to talk about something else, right? It's kind of abrupt to some other things. And actually we have more formal definitions for the 5 levels. For example, the this kind of lowest level is usually about yes, no responses to some binary questions and give some uninformative answers. And usually this kind of answer we kind of don't want, right? And for low level of initiative, usually it's some responses to some close-ended question without extra information. So no extra information is provided. Sometimes it's hard to continue with the talk, right? Continue with the conversation. And we also have medium level. For this one, it's responses to some open-ended questions, and the responses are that share some unprompted information. So sometimes the information is not required, but we provide. So this kind of response is a kind of medium level, and the high level is kind of the response contains some like questions. We want to get some new information from the other part, and sometimes with combining, requesting a topic naturally, blah, yeah. And also we have abrupt ones. So this one is like commanding, requesting some topic unnaturally, and sometimes it's about complaints, right? So you see a lot of different levels. For those things, actually asking questions and the requesting topic naturally is a kind of a very important. So that's why continually we were talking about learning to ask and the topic shifting. So you see, learning to ask actually can be conceptualized in 3 aspects regarding the input, focus, and the cognitive level. Like this one, inputs, focus, and cognitive level. So for inputs, most of us just focus on text, right? But however, it is sometimes also involves images and also give some information about some knowledge base or some outside knowledge. And for the focus, there are 3 important questions to answer. Like when to ask the question, right? Determine the correct time. And also what to ask, right? If you want to ask a word. So the content of the question, and also how to ask the question properly or in the correct context and in the correct style, right? And Regarding learning to ask, actually, there are also cognitive levels, remembering, understanding, applying, analyzing, blah, blah. So it's from the lower level to more higher level. And first of all, like when to ask. So this one actually have a lot of scenarios, like when we browsing online in some shopping app, right? Sometimes you constantly query the system and the browsing again, and just cannot find the correct item. So this one, if we have a chatbot that can observe your interaction session and also your purchase history, maybe if there's an agent that can question you, ask some clarification questions, maybe it can be very helpful for you to reach the target item more kind of like in faster pace. So you see currently we see a lot of conversational, recommendation systems, which is that whenever you go to the e-commerce website, directly pop up a question asking you and chatting with you from the very beginning to the end, right? Which is actually not so natural. So suppose we have a chatbot that can decide when to ask and also what to ask. It might give us a better kind of experience and the result. Also, regarding what to ask, here we actually have two broad kind of methods. I don't go to the detail here. I just introduce here very briefly. We have rule-based methods and also neural-based methods. So for rule-based methods, basically we have two types. One is transformation-based, which means that basically we have something we want to ask, and then we kind of transform it into like kind of some question format, right? So it's kind of apply some predefined linguistic rules to transform a declarative sentence into a interrogative sentence. So this one is from a declarative one to interrogative one. And also we can have template-based methods as filling up some predefined question templates. Yeah, we have the process like this, right? Some content selection, those are select some contents we want to ask, and then kind of construct the question and then ask the question. Also for question ranking, right? Do some post-processing and also do some evaluation. And also we have neural-based methods. For this part, actually, this one is a little bit outdated, like use the sequence to sequence use RN. But nowadays we have like transformer, like GPT, a lot of more advanced models. But the thing behind this is still the same, right? Given the input and then decode the output. So regarding the from shallow to deep, we also have a lot of data sets here, right? We have a shallow question generation, which is just give a single sentence. We don't require reasoning. We don't require some prior knowledge, and then do some syntactic transformation. Then we can get the question. And we also can do some deep question generation. This one involves given a knowledge base, maybe, or say knowledge graph. We do some kind of multi-hoop reasoning over the graph, and then the evidence is usually some multiple sentences, right? And then require reasoning, and then this one doesn't require some prior knowledge yet. But here, deep question generation, this one is usually kind of a human-raised questions, is more hard. So here, usually the evidence is Intel input source, and we will need to require reasoning over multiple pieces of information and require prior knowledge. So this one is the data set. Those are the data set for the multi-hoop reasoning. And also for simple ones, we also have some public data sets and are popular. So for learning to ask, as I just mentioned, it have a lot of work in conversational recommendation. So this is the scenario, right? Suppose the user say, would you please recommend me a movie? Then when the agent is not so sure, it might need to ask back some question to get more information. Like, what is your preference on the genre of the movie, right? You can more information. So how did they do this? I just very briefly go to the structure, right? 3 stages. And then the first one is doing some policy decision, right? Given the input from the user, or say the state we kind of parsed already, then we directly decide what dialogue action to make. Is it ask a question or generate a recommendation, right? And then for this part, the knowledge graph-based preference mining, it is actually given a knowledge graph, and the user, it will traverse over the graph and select out some relations for the response construction. So suppose it is asking a question, then the relation selected will be for the question generation. Suppose the action selected is a recommendation, then the relation selected is for recommendation generation. And then after we give the results, it will go through the natural language generation, give the final result, final response. And also we have some reaction decision. Those one are for the kind of simulation process. After we give the output, compare with the user real output, and then kind of update the state. So it's a kind of a whole loop, right? So yeah, beyond this, we also have a target-driven conversation. So this one is more on the topic planning part. We give you an example here, right? So sometimes the agent chat with you. We can give the agent some target and then let the agent chat with you and guide you towards the target. So this is why it's a more kind of advanced setting. Suppose here we give the agent the target as ebooks. For example, I want to selling you some ebooks and then chat with you. The user say, hi there, how are you doing? The user say, not so good, I'm really tired, right? And the agent say, oh, I'm sorry to hear that, why? At this stage, you don't know the target yet, right? You chat with the bot, but you don't know anything about the agent's target. And then you see, I have too much work to do. And then the user say, because here it's talking about the work, right? Then the agent asks, what kind of work is it? And then the user say, I'm writing a computer program. And then program is kind of linked to book, right? The agent will directly ask, interesting, I read about coding from a book. So it's kind of towards the ebook. And then the user said, really, you are smart. And then the agent say, I prefer ebooks over paper books though, right? So now it gradually guides you towards the targets. So here, yeah, you see, in this work, actually it's like 3 years ago, right? They are doing like chatting naturally with human and proactively guide the conversation to some designed target subject. And how did they do it? In this work, they are using some coarse-grained keywords like those highlighted here, right? And to control the intended content. So how did they do? I provide more information here, right? So first, they drive conversation towards the, actually we have 3 parts, right? You see, this is the utterance, conversation history. We have the target, which is the dance. And then we have the turn level keyword transition and also discourse level target guided strategy. So which means the system consider discourse level and also turn level. In discourse level, they kind of doing some planning, right? From the current state, it will plan a path towards the target. And then after the discourse level, in the exact turn, they will come to select the keyword. Right here, sports and then music, blah blah. They kind of choose a keyword, and then use the keyword together with the conversation history, and retrieve some response, and then kind of modify and give you the final response. So this is the how they do this. But actually, we have more information. If you are interested in this kind of target-driven conversations, we actually, we don't have enough time to go through all of them, but at least the paper here, right? This is the first work I just introduced, right? The target-given open domain conversation. And we also, in the next year, there is another paper in the same thing, right? But they do some kind of improvement. They give a graph. Before we just step-by-step pass, right? Now they are doing this over a graph, they construct a graph. And then do an improvement over the transition, the topic transition smoothness. Before, if we just do step by step, maybe not so smooth. But this one, they construct a graph, then it's kind of planning over the graph, maybe more smooth. And further, there is another work continuing doing this, right? They can do more than one topic transition. So it's kind of making it doing several topic transitions at the same time. And I think that the last year, maybe there are also some works about this, but I didn't keep up. So if you're interested, you can looking over those papers also. And yeah, I think that's all for proactive ontology expansion and the learning to ask and topic shifting. Yeah, thank you.
Thank you, Li Zi, and thank you, Sir Shira. So I'll be quick. That's fine. Yeah, maybe. Right. So so the first part, we have this introduction and kind of motivating. We want this proactiveness for conversational agent. And the second part, we talk about like this like 3 major strategies that leads to talk about. The first one, so suppose you have ontology and then you want to expand a little bit while your agent, so leverage existing knowledge base, expand your ontology a little bit. So that's what we call a little bit proactive. The second part, so it's more focusing on, I think, you know, the agent will ask a question for clarification at a very basic level, or will purposely do some kind of topic shifting, you know, like while analyzing your intent by clustering or whatever along the path, and then, you know, will purposely lead the conversation. Like last one, I think is very cool, the target-driven conversation. So it's like the agent will have an agenda. You know, it's like they will have an agenda, which probably not in the user's mind before you start a conversation, but it's trying to insert this idea about you should buy an ebook in your mind. Okay, so it's become scary. And the third part, the third strategy I'm going to talk about, it's this kind of uterine generation. Yeah, so it's a more like a reinforced learning style. So the agent will trying to figure out what to say at the uterine level, as well as like what kind of like dialogue act. I think dialogue act overlap largely with like intent and slot. So basically, and they will fake it and not actually coming from ontology or whatever, just from like free text and training. So that's what I'm going to talk about as the third strategy. So counterfactual uterine generation will proactively expand the scope of the conversation. And like the dialogue acts, I mean, including slots, value, and lexical choices, as you experience from ChatGPT, I think, right? And those dialogue acts, or this, you know, what's the next word to say, they actually will usually be formulated as like a state space or action space, right? If you think about like what just now, like Lisa present as, at this moment when we should decide, you know, we'll align the cluster. And this action of aligning the cluster, or kind of like choosing the weights for the cluster or grouping them into groups, that actually can be modeled at a higher level, like meta level of algorithms, which is like reinforcement learning. So then they become these parameter settings or actions for the reinforcement learning algorithms. Okay. And the word counterfactual, that means it's very important for the agent to expand a little bit more. Expand means it will trying to imagine something, you know, still within the state and action space. You know, if you tell me that, you know, I can use all the English words, then that's my entire action space, basically, right? But may not in your ontology or not in your knowledge base, but I freely can use, you know, like English space, English like vocabulary, and they will make up some things from this very large state and action space. So the counterfactual means, you know, those slots, those intents, and the lexical choice could be fake. Fake in terms of you never seen that in your ontology or training data, but it's still English word. Okay. The prompts, you can see the agent are actually given more freedom. Yeah, a lot of freedom. They can actually do this kind of very freestyle exploration of topics and ideas. And if they're smart enough, they can also proactively kind of do some anticipation of maybe you will want it, and then the agent will wait for you like 10 hops away, something like that. And it's very easy for them to also diversify like the topics, because the parameter choices could be, just random. So they can do. And if it does right, although it's very hard to get does right, but if it does right, the agent can appear very smart and give you stimulating ideas to, for better conversation and decision making. The cons is to achieve that is very hard. So, people complain about like ChatGPT, for example, they're talking hallucination. So I would think that's just basically the thing I was talking about just now. Okay, well, we want them to have that freedom and producing that kind of stimulating actions, dialogue acts with us, and we want it to under control. So those things cannot be out of control, but it's still very hard. So technical challenges. So first of all, I was talking about just like English vocabulary, but it can be like more relevant sources of this faked data that you can fake it from. And error control and overestimation that actually embedded in the algorithms itself. So all those cons, actually, they can happen in various types of conversation agent, but they look more severe in reinforcement learning because they actually have more freedom. So my part will mainly focusing on the reinforcement learning based agents. So what is reinforcement learning and what make them different? Since the agent, that agent will learn from some environment. In conversation, this environment could be the user, or the user and the agent can form a team. So they actually have an actual task to solve or whatever, so it could be like, the real world, right? It could be the environment as well, right? And the key thing is that it learns in the loop, right? So it's actually not stopping like in supervised learning, it will stop learning and it gets the real words from the environment. So it's very important for the agent to get some correct feedback. Yeah. I kind of feel like to introduce what the agent, doing and what the state and action is actually, if you think about self-driving car, is actually a better way to think about it than a conversation. Yeah, so I'm going to introduce you. So the environment, the learning environment or your domain will be something like this, right? So it's some kind of environment that will give you, and if you hit the road, then you will the agent will have a real penalty. And the agent is able to, see, like observing the environment, and the actions will be, for example, how much my wheel should turn, like 19 degrees or something. Whether I should, step on the gas or the brake. So that will be the action. And for language, in the language domain, that will be which word to use, or should I care about this thing turn or not? So that's the action space. And so the agent has to sampling some action. That means it must try. It must try and error. It must try some reasonable and unreasonable actions and trying to get a real experience. So whether the user you would like it or not. Okay. And then it will finish its learning. And at the same time, some models, they will also trying to, at the same time, not only building like a kind of strategy, what I should react as a conversation agent, but at the same time, they're trying to form understanding about their environment. So like just now I said, the environment can be user or the real task, right? So at the same time, they're trying to learn a user model or, the task modeling. So they're actually doing two learning, the model learning and the policy learning. And I often find that a real misunderstanding happening when I talking to like experts from like supervised learning is that, so for reinforced learning, it's like you're training your agent like a baby and knowing nothing about what to do. And you train them for like, for example, 18 years, and then they graduate and they become adult. Okay, so this is the training process. And then similar to supervised learning, and now you will stop this training and you just let them to go out to deal with the world. Okay, so there's still this training and testing phase for reinforced learning. Okay, so it's not like, oh, I'm learning well trained. No, you actually have to learn a lot, and then you go out to keep interacting. Maybe you will learn a bit, but maybe it's already fine. Okay, so think about ChatGPT. ChatGPT is being trained, I think, continuously for several years. Think about it, like GPT 1, 2, 3, 3.5, and now. Okay, so and it's keep learning, right? And that's why I think it will become smarter. Okay. So so when we're talking about reinforcement learning here, most of the things I was talking about is actually we're assuming your agent is learning from scratch, but in reality, you actually train someone. The agents keep training it based on some already trained model. All right. So I'll is being like using ChatGPT. There's very quick. I want to make it different. So like transformer, we know that's a transformer based model, and this transformer is like its brain, the physical structure. Okay, so fortunately it works. Okay, it could be some other structure, and so it's this part, right? So it's being used like to handle like multiple domains, right? But what reinforcement learning adds in is adding another dimension, right? So I was thinking more now it's like a 3D learning, adding another dimension of learning in time. Okay, so you can imagine that this is one transformer brain, but then it adapts, and it's just keep learning. It's keep learning. Okay, and because one more dimension is being added, right? So it releases huge power of modeling and learning. Yeah. I think I'm going to just yeah, I have to skip most of the things, unfortunately, right? So when we say like we are adding like a counterfactual data into a reinforcement learning based conversational agent, there's like several ways to add this faked data. Like for example, you can but most of the work are actually faking the environments. Right? So one of this problem I think for the agent to learn is that it's getting very few positive feedback. So a lot of this rewards you get are actually they're not very good, right? I mean, because the agent's doing so many try and most of them are actually failures. So we will have this, we do want to have more positive rewards in the interactions. So how, and then we can, generating some. So the generation could be based on what you have already, positive experience and generating some neighbors from it, and then you reuse the label. So that's like one way. So that's like kind of, generating the documents. Another way is you can try to learn the environment. So it's like kind of building some kind of simulator. They understand the user, okay, and have that user behavior model. And then, well, of course, we use a neural network. So basically, this is one way neural network that trying to model the user. And then we can diversify it. How to diversify it, just change the parameter settings, randomize the parameter settings. So it's kind of when your network of your user modeling becomes several different users, right? So now your agent is able to, dealing with multiple users, and even though those diversified guys, they're fake, but it's still quite effective. So that, your dialogue agent will have like more learning experiences, something like that. Okay, so that's really quick. And then I want to talk about another very important issue about conversational agent, especially I think for proactive ones, which is the response quality control. Right. Are you done? Okay, 1 minute. Right. So of course they can say like offensive words. Yeah, they can say offensive words. And that very important thing is they can have this imposter effect. That means they will bluff, right? That actually comes from some of this overestimation part. I think for like toxic language, as you can imagine, we can choose the training data to be cleaner ones. We can also have this toxic language classifiers and trying to detect and remove that, right? Or you can do human labeling like ChatGPT does, right? So yeah. Imposter effect, or this issue of overestimation, is when something good happen, right? Some good reward happen, and then the agent will tend to repeating them. Will tend to just always choosing them, or very easily to believe, some action with a high reward. And that's actually embedded in the reinforcement learning algorithm, because it's argmax, it's looking for something maximize the reward. So it will whenever you have a good reward, it will trust you. Will trust the training data. So it will actually, if you do nothing, it will always almost looking like a imposter, right? So the solution is actually trying to, we'll add some like regularization terms, like regularize the policy. Basically, you see the minus some kind of like distance from more reasonable ones, or yeah, I guess that's it. But questions. But I'm since I'm here, and if you're interested in this part, I'm very happy to answer a question. Some quick questions. Or no? Like conservative reinforcement, you can add some, some penalty term to make sure it won't overestimate. So this is very hard to get rid of, because that's part of this learning mechanism, because you want to, as agent, you want to be a good agent. It means you want to maximize the reward. But if you keep maximizing, you will become a bluffer. Yeah. So the solution actually quite a mathematical. I think I'm done. And thank you so much for your attention.
Sorry about that. I just enjoyed too much in the talk, so I give Grace too less time. Yeah. Sorry about that.
Yeah, I just want to say, and yeah, we really needed a lot more time, but we are all around. This is not even the first day of the conference. We are all around for the rest of the conference. So feel free to come talk to us. I'll say one last thing, to wrap up. This was about proactive conversational agents. The thing about proactiveness is, on one hand, we want these things to be smart and proactive, but at the same time, when you train something to be smart and proactive, they could also misbehave. And so a lot of things is sort of a balancing, right? And so what Grace was talking at the end, it's actually, those are very important issues. How do you make sure that they don't hallucinate, they don't come up with like toxic messaging and so on? So as we work towards this, just keep this in mind, that it's not simply making them proactive, but also making them responsible in some way. So I think that's where current state of the art is, that as we see this ChatGPT and BART and other things, they are getting proactive, they are getting smart, but then they're also creating all these issues. And it's a question of how do we do both? How do we make these smarter and also keep them contained in some way so they're not creating harms? But a lot of these questions are still open. So I think it's a great time to be working in this area. There's a huge demand. There's a trend that's set up. that will call for a lot of research in this domain. So we are all excited about it, but of course we are biased because we are already working in it. But I hope you are also excited about it. Come talk to us. Happy to chat over the lunch, coffee breaks, and over the next few days during the conference. So thank you so much for coming, and wish we had more time, but we don't want to stop you from having your lunch.